Greetings everybody, how are we doing? Are we well? Can you hear me and can you see me? If you can you put a big fat plus in the chat? Hello, hello, hello. I'm sure everybody's pumped to do some chemistry this afternoon. It's a lovely sunny afternoon. Perfect time to brush up on our chemistry skills. Hello, hello, hello. Are we ready? We're a bit early, so give it a few minutes. Make sure everybody's here. Hello. How are we doing? Hello. Yubi, greetings. How are you? Sazad, hey, how's it going? How are you guys doing? Are you well? Well done for turning up at 4:30 on a lovely sunny Wednesday afternoon to do some chemistry. Siani, greetings. How are you? So which part of the UK are you guys from? Let me know in the chat. And by the way, can you hear me and can you see me? If you can, just put a plus in the chat as well. Manpreet, why is there a secret lesson? Because you love chemistry, that's why. You ready? From London, same here, same here. Organic chemistry, I have to say, it's not my favourite, but I still like organic. Probably say inorganic's my favourite. Transition metals and all that stuff. Which is why we're going to start with the transition metals question. So, before we do that, yeah, you've got double chemistry, mate. Manpreet, you've got double chemistry, so can't get enough of it. So before we actually get into the chemistry aspect of it, my name is Divin Debachu and I'm the assistant head of chemistry here at my EdSpace. I'm a fully qualified chemistry teacher and have over 8 years of teaching experience in the classroom. So I graduated from UCL, University College London, and graduated with a BSc in chemistry and got a first class degree. I was top 3 in my year as well that year. And a sort of highlight of my teaching career, I guess, was that in 2023, almost 50% of my students got an A star or an A. So really top marks in that year. And they did a fantastic job. They absolutely smashed it. That's a very brief background about me. Any questions to do with this slide? If so, just fire away. See, very smiley because I'm reading a chemistry textbook, the best type of book you can read. If not, let's go. Actually, there's one thing missing from here. After my bachelor's, I stayed on at UCL and did an engineering doctorate, an EngD, which is equivalent to a PhD in chemistry, and that was in inorganic chemistry. So you're in safe hands. Okay, introductions out of the way. Let's get cracking. So we're going to be looking at transition metals first. So I've put down that this is AQA or Edexcel. Can you let me know which exam board you guys are doing? Let me know in the chat, just so I have a clue of what exam board you guys are doing. Most people do AQA or OCRA, but I know there are a few Edexcellers in here. Cool. Siani, this isn't on your spec, but it's still very useful, okay? So if you're doing AQA, you definitely need to know this, and if you're doing Edexcel, you definitely need to know this. Okay, so, question for y'all. Why do we get coloured complexes when we're looking at transition metal complexes? Fire away in the chat before I answer the question. So let's say I've got hexaaqua copper 2+, so Cu, H2O6, 2+. And that's aqueous. Why does that appear as cyan? Partially filled d orbitals. Okay, so we've got a copper 2+ ion. We've got a copper 2+ ion. And what is the electron configuration? Now, if I account for the core electrons by using the electron configuration of argon, which is 18 electrons, how many 4s electrons do I have? And how many 3d electrons do I have? Fire away in the chat, please. Oh, wait. What are we going to say? We'll use this as an example, okay? Any suggestions? Yeah, 4s03d9. Good, let's check that because... Alright, so if we have normal copper, that would be Ar4s1, 3d10. And then remember, when we remove the electrons, the 4s ionize first, so that goes to 4s0. Then we take 1 off the 3d10, and that gives us 3d9. Absolutely, that is correct. Okay, so then what we're going to do is, we have our 3D orbitals here, and they are degenerate. Does anybody know what we mean by the word degenerate in this context? So these are my 3D orbitals. And this is energy on the vertical. They all have the same what? They all have the same energy value, right? So let's put these electrons in. That's what we mean by degenerate. So we're going to put 9 electrons into these 3D orbitals. So 1, 2, 3, 4, 5. So remember, they go unfilled first. So they go into empty orbitals first before they start pairing up. And that's Hund's rule. And then they start pairing up. And look, we have got a partially filled d orbital. So this satisfies our definition for a transition element, okay? So it forms at least one stable ion with a partially filled d orbital. And copper 2 plus is a transition element, okay? So what happens next? So let's draw this little complex out. So what happens next? Let's draw this complex out. What shape is hexaqua copper 2 plus going to be? Fire away in the chat. Do we all agree it's going to be octahedral? Because we've got 6 ligands, so you've got 6 water ligands bonded to it, this is going to be octahedral, okay? This is going to be octahedral. So let's put our ligands around the copper center and show that it's a dative or coordinate bond because it bonds through the lone pair of electrons on the oxygen atom. And these are all monodentate ligands, and the coordination number here is 6. Okay, any questions so far? Everybody happy? Good bit of revision. And then what happens is, it's really helpful looking at it this way, is inspect these orbitals. You don't need to know these orbitals, but it's really good for visualizing what's going on. So, in the 3D orbitals, we get the 3 dyz, the dzx, and the dxy. And if we put axes here, so let's say for sake of argument that's the y-axis and that's the z-axis. So what can you say about the electron orbitals? Are they actually on the axes or in between the axes? Do they lie directly on the axes or are they in between the z and y-axes? Say what you see, just like catchphrase. Yeah, they're in between, absolutely. So the orbitals are in between the axes, and that is true for the dyz, the dzx, and the dxy, okay? However, what's different for the dz squared and the dx squared minus y squared? How the orbitals range differently? They're not in between. Where do they lie on these axes? If we inspect that diagram or drawing, they're actually on the axes, okay? So these guys, in the dz squared and the dx squared minus y squared, the orbitals are literally on those axes, okay? So the orbitals, we say, span the axes and they're not in between, okay? Now, follow-up question, what is in these orbitals? What do these orbitals contain? Not a trick question. Orbitals are a region of space or a volume of space where we're most likely to find the electrons. Absolutely. Okay, so look what happens when the ligands actually bond. So imagine, here is our drawing. I'm going to superimpose it. I'm going to superimpose it onto the dzy orbitals. So look, here is my ligand and it bonds to this copper center, okay? Now, these d orbitals are the orbitals of the transition metal complex. The electrons coming from the ligand, are they going to interact very much with these orbitals that lie in between the axes, yes or no? I mean, there's going to be some interaction between the electrons, but is it as much as if they interact with the orbitals that lie on the axes themselves? Which one are we going to get more of an interaction with? So we're comparing the electrons on the ligand versus the electrons in the transition metal. So are we going to get more of an interaction of the ligand electrons and the transition metal electrons when the orbitals are in between the axes or on the axes? Yeah, absolutely on the axes. Look, if I superimpose my rubbish drawing, look what happens. You've got the ligand electron pair that is directly almost interfering. Firelord, ta-ta. Right. So here is the ligand electrons, and those are interfering directly with the orbitals on the transition metal center, right? So there's going to be more of an interaction with the dz squared and the dx squared minus y squared. So if we give these guys labels, let's say that's dyz, and let's say that's dzx, and let's say that's dxy, and this is dz squared, and this is dx squared minus y squared, which orbitals are going to feel more of a repulsion? Is it going to be my dxy's or is it going to be my squared ones? What say you? What do we think? So when the ligand bonds, yeah, absolutely, it's going to be the squared ones. So when the ligand bonds, its electrons interfere with the transition metal electrons more when those orbitals are on the axes rather than when they're in between, okay? So what happens is we get splitting of the d orbitals after bonding. So we get 3 orbitals going below and 2 orbitals going above. This is a level. Right, so I'm going to label these as dyz, dzx, and dxy. So those get pushed down in energy. These get more stable. More stable as less repulsion between ligand electrons and TM stands for transition metal ion. Okay, well if these guys are more stable, why do these other ones, the squared ones, get pushed up in energy? So why are these ones raised in energy in comparison? Because they're less stable. Why are they less stable? Okay, but let's use a converse argument, right? So these ones are going to be less stable as there's going to be what with respect to repulsion? Is there going to be more repulsion of these guys or less repulsion of these guys? Yeah, absolutely. There's going to be more repulsion between the ligand electrons and the transition metal ion. So that's why they get repelled more and they get pushed higher up in energy. Whereas these guys, because the orbitals lie in between the axes, the interaction between the ligand electrons and the transition metal electrons is less. So these guys get pushed down in energy. Okay, so that's why that splitting occurs. 3 go down, 2 go up. So now let's populate this with electrons. So we've got 9 electrons to fit in. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, this splitting of energy corresponds to what? AQA and Edexcellers? or the splitting of the orbitals corresponds to an energy gap, delta E, which is equal to what? Yeah, absolutely. So that difference in energy between the lower energy state and the higher energy state is equal to Planck's constant multiplied by what? Yes, h nu. Good. Or if you want to say hf, say hf. Whatever works for you. Okay. So this energy gap corresponds to visible light frequencies. Okay, so what happens when a photon of visible light hits it? So let's say we've got white light coming in. I'll do it in blue. What happens when a photon smacks an electron from a lower energy orbital? What happens? Yeah, absolutely. So we get absorption. And what does the absorption result in? So we get absorption. So let's put that in. So we get absorption at a particular frequency. And then what happens to one of these electrons in the lower energy state? What do you mean, the ones that are absorbed on... Okay, yeah, I see what you mean. Yeah, so we get a DD electron transition. So let's say, for sake of argument, this guy, which I'm going to highlight, gains some energy and it gets promoted into a higher energy level from that absorption, okay? And then, if this is our eye, what we see is, we see the complementary colors. So we observe the complementary colors that are not absorbed, and therefore they are transmitted or reflected into our eye. There you go. So, just to recap, we get absorption of a particular frequency, okay, of visible light. Then we get a DD transition. So, one of these electrons gains that energy and it is excited from a lower energy state to a higher energy state. And then those frequencies that are not absorbed are transmitted or reflected into our eye, and those are the complementary colors. So, that's why transition metal complexes are colored. Any questions on that? Are we happy? Let me know in the chat. Can you put a plus in the chat if that makes sense? And has anybody ever shown it to you like that? About why we get that splitting? Hopefully that makes a little bit more sense about why we get the 3 below and 2 up. Cool. All right, let's go. All right then. Follow-up question. Why do transition metal ions form coloured complexes? What do we have to say? So we're putting this all together for an exam question, and let's use as few words as possible. So what is the first thing we're going to say? That the d orbitals do what? What word goes after d orbitals? One word. Like strawberry. So the d orbitals split after the ligands bond. You don't even have to say that bit, okay? Not partially filled just yet, okay? So the d orbital split after the ligands bond. You're getting marks for saying the d orbital split. And then the energy gap corresponds to what frequency? So the energy gap corresponds to visible light frequencies. And then what? And then we get absorption, which leads to what? So absorption of certain frequencies. Yeah, absolutely. Nice, Zad. Absorption of certain frequencies of light results in an electron being promoted from a lower energy orbital to a higher energy orbital. Okay, and what's the last marking point? What's the last thing we need to say? So we're kind of there. Almost there. Anyone got an answer here? So we're going to say, we've talked about the d orbital splitting. The energy gap corresponds to visible light frequencies. We get absorption of certain frequencies of visible light. That results in a DD transition. And then the last thing we have to say is that frequencies not absorbed are transmitted or reflected into our eyes. That's it. That's where the marking points are coming. Okay, so if you're doing AQA, you also need to determine what the energy in joules is gained by each excited electron in a particular complex. So we said that the energy gap delta E is determined by HF. So H is Planck's constant, and that's given to us. C is the speed of light. So if I need to work out the energy, how am I going to do this? Where do I go? So I need an equation from GCSE physics which contains the speed of light and frequency and wavelength. Does anybody remember what that equation is? So C equals F lambda. Okay. Yeah, so C equals F lambda. Absolutely. So if C equals F lambda, how can I rearrange that for frequency? So frequency equals C over the wavelength. Happy? So then what I can do is I can substitute that term in to here for frequency. So then this becomes delta E equals HC over lambda. And I'm going to use that equation in the red box. Okay, so what terms do I know? I know H and I know C. Do I know the wavelength? Yeah, I know the wavelength because it's given to me in the question. It's absorbing at 490 nanometers. So I know all of these terms. So now let's bung them into the equation. So delta E equals Planck's constant, which is 6.63 times 10 to the minus 34. Multiplied by the speed of light, which is C, which is 3 times 10 to the 8. All over what? The wavelength that was absorbed, and the wavelength that was absorbed was 490 nanometers, but I can't just put 490 in. What do I need to do to my wavelength here? I need to convert this to what? Yeah, I can't just use 490 though. What do I need to do? It's in nanometers and I need to convert it to meters. So nano stands for 1 times 10 to the minus 9 of a meter. So I need to times it by 10 to the minus 9 to get it into meters. And if we process that, what do we get? We should get 4.059 times 10 to the minus 19 joules. And there is your answer. So that is quite a tough question. 6 marks. 3 for this wordy part. And 3 marks for this. Any questions? Are we good? Sazad, you good? All right, let's move on. Okay. This is quite a tough question, actually. So it might take up the remaining part of the lesson, actually. Let's see how we go. So this question is about compounds containing ethane dioate ions. Now, when you see that word ethane dioate, that is derived from what? Seems easy. You got this. You got this. No stress. In fact, this is for all of them. AQA, OCRA, Edexcel. So, Manpreet, ethane dioate ions. What are they? Or anyone for that matter. They're derived from ethane dioic acid, and ethane dioic acid looks like this. So we've got 2 carboxylic acid groups joined together. That's it, okay? So that's ethane dioic acid, and then the ethane dioate ions. What we're going to do is we're going to deprotonate, we're going to lose that proton, and we're going to lose that proton, okay? So if we deprotonate here and here, we will generate the ethane dioate ions. So imagine I come along, take that proton off, and I take that proton off. Look at what's going to be left. I'm going to have a negative charge here, and I'm going to have a negative charge here, and this is my ethane dioate ions. Cool. So let's think about what's happening. So a solid sample contains a mixture of sodium ethane dioate, Na2C2O4. And it also contains ethane dioic acid dihydrate and some inert solid material. What do we mean by some inert solid material? Some solid that isn't doing any what? This stuff is not reacting. It is inert. So it's not reacting. Absolutely. Correctamundo. And then what we're doing, we're taking this solid, and we're dissolving it into a 250 centimeters cubed solution. And it's given us the mass of solid that we're dissolving in that volume of water. And then we do 2 separate titrations using this solution. In the first titration, we take a 25 centimeter cubed sample of this prepared solution, pipette it into a conical flask, add some acid. We heat it up, get the reaction going, overcome the activation barrier, and we do a titration with potassium manganate solution. And it tells us the amount required for the endpoint. Okay, the fact that we're doing a titration with potassium manganate, what is this telling us? What type of titration is this? Titration with potassium manganate. Okay, is it an acid-base titration or is it a redox titration? What say you? Yeah, it's redox. Absolutely nice, Grace. So this is a redox titration. Okay, and then let's continue reading. In the second titration, we do another titration with another 25 centimeters cube portion with 0.1 sodium hydroxide using phenolphthalein as an indicator. Okay, so in the second titration, what's going on? Is that redox or is that acid base? The fact that we're using KOH, or sodium hydroxide in this case, and we're using phenolphthalein as the indicator. So this one here. Acid base or redox? What do we say? Pick one. Got fiddy. Yeah, absolutely, it's acid base. Okay, so now we need to determine the percentage by mass of sodium ethanedioate in the original mixture. Okay, if you've been in my classes before, has anyone been in my classes before? I know Manpreet has. What am I going to say that we should do? We should ideally draw a what, especially as part of our revision. Before we start putting numbers everywhere, we should ideally draw a storyboard. So let's draw a storyboard. Okay. If you've got a bit of space or you've got a bit of paper, let's go. So, here is my solid. I have 1.9 grams of solid, okay? And in that solid, I have got a mixture. I have got a mixture of 3 different substances in effect. We don't care about the inert solid, but imagine I'm drawing it in, okay? So, this part I'm going to shade. That's going to be my C2O42 minus ions from sodium ethanoate. Sodium ethanedioate, I should say. And then, what is this section, which is unshaded? What is the unshaded section referring to? So I've taken account my C2O42 minus ions coming from sodium ethanedioate. And what is that section referring to? The bit that undergoes the acid-base reaction. So that section is H2 C2O4. Okay, so this is my acid. Yeah, the dihydrate, absolutely. And this is my ionic salt. Okay, so here's my ionic salt in green. The other part is the dihydrate, the acid. Okay, so then what do we do to this solid? We dissolved it in 250 centimeters cubed of water. So that means volumetric flask. And then we took out a tenth. So we took out a portion, we took out a tenth. So we're going to have a tenth of the number of moles in this conical flask. So in here, we're going to have a tenth of the number of moles. Okay, and then we did a titration. In the first titration, what did we use? What's in the burette that we have information about? It's a purpley colour. Anyone? What do we think? Yeah, absolutely. So we've got MnO4 minus. Good, we've got the manganate. Now I know some information about the manganate, which it told me in the question. I know the volume. Can anybody remember the volume? For the titration, it was 26.5 centimeters cubed. And then the concentration, I believe, was 0.02 moles per decimeter cubed. Okay, so where do I go next? So I've got my little storyboard and we do a second titration, but we'll work from the first titration. So what can I work out if I know the concentration and volume of the manganate ions? And this is a solution calculation. I can work out the number of moles because N equals C times V. Absolutely, you got it. Nice, Grace. So N is this. Yeah, we're going to go backwards. So we've got the N is a symbol for the number of moles. Yeah, well, not the moles in 25. Yeah, if we go backwards. So the first thing we have to do is work out the number of moles of manganate in the burette. Okay, so the number of moles of manganate in the burette are going to be what? 26.5. I need to divide that by 1,000 to get it into decimeters and then multiply it by 0.02. So what do we get? Fact. Can you see if I get the calculator up? So we'll do it in real time. So 26.5 times 10 to the minus 3 multiplied by 0.02. Do you all agree we should get 5.3 times 10 to the negative 4? mole. Okay, cool. So I've worked out the number of moles in the burette. So now, how do I work out the number of moles of the ethane diawate ions in the 25 centimeters cubed conical flask? So step number 2 is, now I need to work out the number of moles of C2O42 minus ions in 25 centimeters cubed. How do I work that out? Well, I need the chemical equation. And if we have a look, what is the molar ratio between the manganate ions and the ethane diawate ions in this redox titration? It's 2 to 5. So, to work out the number of moles of ethane diawate ions, I take 5.3 times 10 to the minus 4, and then I divide by 2 and times by 5. Hi, preppy queen. So divide by 2 and times by 5. Does that make sense? We good? So let's show that. So we should get 1.325 times 10 to the minus 3. So where did I get that from? That's just the molar ratio. So that gives me 1.325 times 10 to the minus 3 mole. You did actually, yeah. A bit more advanced than Key Stage 3, but fair enough, you're here. So let's learn something. So then, where is the 5 from? Okay, so we're looking at the molar ratio between the manganate ion. So we just worked out the number of moles of the manganate ion. And then I'm using the molar ratio to work out the number of moles of the C2O42 minus. And if you want to think about it like this, to go from 2 to 5, I need to times this by 2.5, which is the same as dividing by 2 and timesing by 5. Cool. So we got the number of moles in 25. Tell me what the next step is. So I've got the number of moles of the ethane diawate ions in here. And remember, you're going to go backwards. So you're starting at the right-hand side of the picture and you're going left. So, done that. Where do I go next? If I go the opposite direction, I need to work out the number of moles in what volume? In 250, absolutely. Times it by 10. So, let's put a label. Now I'm going to work out the number of moles of the ethane diawate in 250. So this is going to be 1.325 times 10 to the minus 3. You'll put timesing by 10, but just as a little reminder, you can do it via scale factor of 250 divided by the smaller volume, because we're scaling up. So this is going to be 0.01325 mol. So that's the number of moles in the volumetric flask. Okay, where do we go next then? This is a tough question. I believe this was just a straight 8 marks from AQA, you know. Straight 8 marks. No walkthrough, no scaffolding. Bang, there you go. So it was pretty awful. But we can get marks along the way. So what is the next thing we do? Any ideas? Can't remember which year. Could have been 2017. Definitely check it out. This is difficult, yeah. I'm not lying. This is a tough question, and it was just straight 8 marks, last question. So they're like, here you go. And that's 8 marks is a lot of marks to just lose on a question, right? So, does anybody know where we go next? Well, I would stop there, and I would say I probably got 3 marks. I'll take that. So then what I do is I look at the second titration, okay? So in the second titration, we've got an acid-base reaction. And then look, I know info about the sodium hydroxide. I know the concentration, which is 0.1, and I know the volume, which is 10.45. So from the concentration and the volume of the sodium hydroxide, what can I determine? Hi Eunice, how are you? So I can determine the what? The number of moles of NaOH. Because I know the concentration and the volume. So the volume was 10.45 over 1,000. Yeah, absolutely. Let's determine the number of moles. And the concentration was 0.1. Okay, cool. So if we process this, what do we get? And I'll do it on the calc. So this is going to be 10.45 over 1,000 multiplied by 0.1. So we get 1.045 times 10 to the minus 3. Mole. So what I've done is, that gives me the number of moles of the hydroxide ions. But look at the molar ratio. Look at the molar ratio between hydroxide and the ethindioic acid. It's 2 to 1. So to work out the number of moles of ethindioic acid, what do I need to do? How am I going to use that ratio? What do I need to divide by? So it's going to be the previous value that I just got, and I'm going to divide it all by what? What do we say, guys? Divide by 2, because the molar ratio is 2 to 1. Absolutely nice as add nice grace. So I'm going to divide that by 2, and if I divide that by 2, do it with me, you should get 5.225 times 10 to the negative 4 moles. Is that correct so far? Everyone happy? So we've probably got like 5 marks. Probably got more than half, right? Just by doing stuff and not even getting the final answer. And that's pretty decent, okay? So don't just give up if you have a question which looks hard on the surface, but actually it's not that bad once you go through it. Okay, so where do we go next? And this is where the conceptual leap comes in, okay? This is where the conceptual leap comes in. So, step number 6 is a tricky one, okay? And the reason for this is, what can happen to my ethindioic acid in solution? I'll draw it for you. And I did it right at the beginning of this question, actually. What can we do to these protons? Proton there and a proton there. What can happen to these guys? Yeah, you can get dissociation, right? And then both of them could be deprotonated, so I generate 2H+. Yeah, ethindioate ions are produced from dissociation. Absolutely good. So I could get 2 protons and C2O4 2- ions. So I could get this. So that means potentially this value that we calculated is actually what? That's the value not just from the ethindioate ions coming from the sodium salt, but also the ethindioate ions coming from what? Coming from the partial what? So we've got ethindioate ions coming from 2 different places. We've got them coming from the acid due to dissociation, and we've got them coming from the sodium salt. Okay, so where do we go from this? What do we do? So let's think about this. Now that we've explained where it's coming from, well, I know what the number of moles of my dihydrate is, right? So I know what the number of moles of that is. So the number of moles of that is 5.225 times 10 to the minus 4 in 25 centimeters cubed. So what I could do, that's in 25 centimeters cubed. I can then times it by 10 to work out how much is in 250 centimeters cubed. And then using that molar ratio, what is the number of moles of the ethindioate ions in solution coming from the dihydrate? Look at the ratio, it's 1 to 1. 1 to 1. So what is the number of moles of here going to be? Grace, I think you're getting there, absolutely. So this is going to be 5.225 times 10 to the minus 3 mole. Absolutely. Okay, so now this value that we got originally of 1.325 times, 0.01325 is too big, right? That is way too big because we've got ethane dioate ions coming from two different places. I want to work out the number of ethane dioate ions coming just from the sodium ethane dioate. So let's write a little equation. So we have got the total ethane dioate is equal to the ethane dioate coming from two different places. So from the salt and the dihydrate. Okay, but I want just the number of moles from the salt. So what am I going to do? How do I determine the number coming just from the salt? Because I've got the total and I've got the number coming from just the dihydrate. So what do I do to work out the number of moles coming just from the salt? What magic do I do with this equation? Yeah, absolutely. Nice. So my total is going to be 0.01325. Yeah, I got it. You got it. You got the right idea, right? That's the main thing. Take away the number of moles coming from the dihydrate, which is 5.225 times 10 to the negative 3. And that gives us the number of moles coming from just the salt. The main thing is, are we getting what's going on? Because this is quite a complicated question. We happy so far? Yay or nay? Cool. So 0.01325 take away 5.225 times 10 to the negative 3. Do you all get 8.025 times 10 to the minus 3 mole into 50 centimeters cubed? So that's coming just from the sodium salt. So I've got the number of moles here, basically. So if I go right back to my storyboard, I've worked out the number of moles coming from that section. Okay, so I know the number of moles of this guy. And what other quantity do I know about this guy that I get from free just from the chemical formula? And I think Grace alluded to it. Because I spent ages working out the moles, so I've got those. But I also know its chemical formula. And if I know the chemical formula, I know the what? The MR. So, absolutely. So if I know the number of moles of ethane dioate, I am sorted. So, now that I know the number of moles in MR, what am I going to work out like a robot? And I'm not going to, don't make me say mass equals Mr. Mole. But mass does equal Mr. Mole. So, to work out the mass, I'm just going to multiply it by the MR. Absolutely lovely. So, the mass in step number 8, we're getting there, is equal to 8.025 times 10 to the minus 3 multiplied by the MR. Can somebody tell me what the MR is? So, it's going to be 23 times 2 plus 24 plus 64 times. And what do we get? Oh, not 88. Grace, I know where you've gone wrong. You've just done it for this section here. You've just done it for the C2O4. But remember, that was coming from the Na2C2O4, right? So it was actually coming from here. So that means you need to take into account the sodium as well. Plus 16 times 4. So if you multiply it by the MR, we should get a value of 1.07. Whew, got there. So, we actually haven't even fully answered the question. To fully answer the question to determine the percentage purity, we're going to divide 1.07 divided by the original mass and multiply it by 100, and that will give us the percentage, which is 56.6, we'll say. And there you go, 8 marks. Pretty much no scaffolding. There's a lot of chemistry going on there. But the main thing is, can we follow? If we could, put a plus in the chat. And does the logic make sense? And by the way, did the storyboard help as well? Yeah? No worries, all good. Lovely. Okay, has anybody seen a question like that before? That's like the hardest redox titration you guys could ever get. Wicked. Really, really good. Alright, when you're revising, I think it's really important to spend a bit of time drawing it out and then annotating it, just so you can figure out the structure of these questions. Now really, yeah, this is a savage 8 marker as well. But don't do it if you don't have time in the exam, because once you've done enough of them, the structure of these redox titrations are pretty much always the same. Unless they do something savage like this and chuck in this 8 marker where you have to think about this last step. But just remember, you can get 6 out of 8 marks by just doing n equals c times v, okay? And scaling up. So don't just look at it and think I can't do it. There's always hope. Alright, I think we're going to leave it there. But before we wrap up today, I would like to share an excellent opportunity with you guys to boost your A-level prep. Remember, Easter holidays is not really a holiday. It's time for you to start doing some revision. So, if you liked what you saw today and you want a special offer, put a plus in the chat. Manpreet, ta-ta. Guys, come on, let's get involved. So if you want a special offer, put a big fat plus in the chat. Let's go. Way, Manpreet's doing double pluses. Get in. Sazad, thank you very much. UB, thank you very much. Who doesn't want a special offer? Never looked a gift horse in the mouth. Wait, we got 4 from UB. Nice, keep up the good work. So, if you liked what you saw today, next month, My Headspace is going to be launching our Easter revision course. Now, our Easter revision course is top quality, and I'm not just biased. It's an intensive revision cram course that's designed to help you revise pretty much the entire curriculum efficiently and learn some tips and tricks, okay? We have maths, further maths, bio, chemistry, and physics courses available. So each course pretty much goes through every single topic, helping you repeat the fundamentals and consolidate your knowledge to make sure that you guys secure the top grades. So right now, we are running an early bird sale. And that means so what is usually £100 is just £20 for one course. Lucky you. And every course after that is only an additional 10 whole English pounds. So for example, if you choose the maths course, it will be £20. If you choose both maths and English for GCSE, for example, it will be £20 plus £10, etc., etc. So 30 quid. What an amazing deal. So if you choose maths and the sciences, it will just be £60, and that's for GCSE, okay? But same applies for A-level as well. So what's exactly included in our course? Each course is going to include 3 intensive 6-hour live revision sessions. Now, if you know me, I'm probably going to go over the 6 hours to make sure you guys get the most out of those sessions as well. Obviously, they're going to be interactive, just like today's session, and be led by expert teachers. All the sessions are recorded, so you can re-watch them every time, okay? Whenever you want to. You'll also have access to mock papers and workbooks crafted by professionals after the sessions, so you're fully prepared for your exams. Who likes the sound of that? Put some pluses if you're happy. UB, we're getting there, we are getting there. So, We've just gone through what's included. 6-hour revision lessons times 3. 18 hours in total. They're all recorded. You get workbooks which are professionally designed by designers, and they're really beautiful. And you also get 3 mock exam papers, plus tips like we had today from experienced examiners, okay? And not only is MyEdspace affordable, more affordable than traditional tutoring, our teachers really are the very best. So MyEdspace selects only the top 1% of teachers from the extensive selection process. So basically you have to resit your A-levels and you have to do an A-level paper during the selection process. And if you don't get above 90%, then it's ta-ta. And all of our teachers are superstars and have hit 90% plus when they were applying for the jobs at MyEdspace. So you really are dealing with some top tier teachers. They know what they're talking about. And just look at the caliber we've got. So look at the caliber we've got. So we've got Queen Mary, Imperial, UCL, University of Oxford, Manchester, UCL, amazing universities, and mainly first class degrees from these Russell Group institutions. And students absolutely love us. We've got thousands of students who have been with us and almost 900 views on Trustpilot with an average rating of 4.7, which is incredibly impressive, I would say. So, what are you waiting for? That's what I would say. What are you waiting for? And have a look at some of the reviews on Trustpilot. Absolutely fantastic. So they learn more in 3 days on this course than the entire 2 years of college. And that's impressive that we can do that, right? So what are you waiting for? Click on the link below. Take advantage of that special offer. If you've got any questions, fire away. How did you find the session? Hopefully we learned something. Manpreet, of course you are. Manpreet's buying. Don't miss out. Don't let Manpreet buy all the chemistry course. Absolutely loves it. He's got another 1 hour and 30 minutes with me after. Lucky. Preppy Queen, will see you there for A-Level Chem. Don't worry about Key Stage 3. It's all about A-Level Chem. Fantastic. Really, really good to hear, Sazad. Okay, any questions? Fire away. Sorry, I just need a sip of water. Okay, if there are no questions, we will leave it there. Thank you very much for watching. Been an absolute pleasure. Click on the link below. Take advantage of that offer. Make some gains in the Easter period. It's mainly water. Thank you guys so much. Can you all see the link though? Yubi, can you see the link? Should be in the lesson description. Yubi, thank you very much. Awesome. That's really great. Click on it. It's unbelievably cheap. It's like the price of what? 5 coffees in London. Make the most of it. All right, we will leave it there. Thank you very much. Been an absolute pleasure. And ta-ta. I'll see you guys for the Easter revision course. Bye-bye.